Today we're going to continue our conversation about estimating parameters and determining sample sizes by talking about estimating a population standard deviation or variance. So we'll be looking at taking a sample standard deviation or sample variance to estimate the value of the corresponding population standard deviation or population variance. So we've got main concepts of point estimate. This is the same deal as it's been. The sample variance is the best point estimate of the population variance, and the same deal with the standard deviation. And for confidence intervals, we're going to be looking to construct a confidence interval estimate of a population standard deviation, and we're going to construct that confidence interval using a thing called the chi-square distribution. So the chi-square distribution, well, what is this thing? In a normally distributed population with variance sigma squared, if we randomly select independent samples of size n, and for each sample, we compute the sample variance, then the sample statistic chi-square, which equals the quantity n minus 1 times the sample variance divided by the population variance, has a sampling distribution which we call the chi-square distribution. So critical values of chi-square. When we're finding these, we're going to have a chi-square to the right tail for our right tail critical value. And we'll use a little subscript capital R to denote that. And we'll also have one for the left tail. So we'll use a capital L to denote that. So these critical values can be found using technology, but again, we're not going to focus on that. Instead, we're going to focus on using table A4, and they require that we determine a value for the number of degrees of freedom. Just like when we were finding the population mean from the sample mean, our number of degrees of freedom is n minus 1, and the reasoning for that has not changed. So this chi-square distribution, why we need this left tail and this right tail idea is our chi-square distribution, it's not symmetric like our normal distribution or our t-distribution were. So the chi-square distribution is actually skewed right. Also, the values for the chi-square distribution, they can be 0 or they can be positive, but they can't be negative. Anything squared can't be negative, right? When we're talking real numbers, that's what's going on here, all right? So that's our chi-square distribution. So also, when we take the different numbers of degrees of freedom, as the number of degrees of freedom increases, the chi-square distribution approaches a normal distribution. Right? It won't be the standard normal distribution because it's not going to be centered at 0, but it gets more of a bell shape that's not skewed right quite as extremely. And you can see this happening in this graph here when we have 10 degrees of freedom versus 20 degrees of freedom. The 20 degrees of freedom has a lot more of that bell shape that we expect from a normal distribution. So because the chi-square distribution is not symmetric when we're looking at a confidence interval estimate of our population variance, it doesn't fit into this format of the sample variance minus error and the sample variance plus error being between those two things. So we have to do separate calculations for our lower and upper bounds for our confidence interval limits. So we'll use table A4 to find those critical values and do those calculations. So in table A4, each critical value of chi-square in the body of the table corresponds to an area given in the top row of the table. And each area in that top row is a cumulative area to the right of the critical value. This is also a way that it's different than some of the things that we've looked at before. So just keep that in mind. And again, look for the picture with the table to help you remember these things. So let's take a look at an example. A simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation requires the left and right critical values of chi-squared corresponding to a confidence level of 95% and a sample size of n equals 22. So we're looking for a 95% confidence interval, which is why we have the 95% thing, and n is going to be 22 since our sample size is 22. So finding our left critical value, this is going to be looking at what's separating alpha divided by 2, in this case 0.05 divided by 2, or 0.025, to the left in the left tail. So we have that here. And the one that's the right, or the upper one, we're looking for an area of 0.025 in the right tail. So the picture of what that looks like here is we have our chi-squared distribution drawn there, and we're looking for these two values that give us the same areas in tails that are different shapes. Because it's not symmetric, it's actually skewed to the right. So our number of degrees of freedom, we'll be using n-1, so 22 minus 1 is 21 degrees of freedom, and using our table with 21 degrees of freedom and looking for a cumulative right area of 0.975, that's 1 minus 0.025, we find that chi-square for our left, which is also our lower limit, is going to be 10.283, and when we're looking for the cumulative area to the right of 0.025 with our degrees of freedom is 21, we'll get our chi-square value of 35.479 to work with. All right, so here's a little bit more detail about finding that one to the right, and a little bit more detail about finding that one to the left that you can take a look at. And now that we know how to find our critical values, we're going to talk through how do we construct our confidence intervals. All right. So we have a whole long list of variables here. Most of them are familiar from the past. So we have sigma for the standard deviation. We have sigma squared for the variance, both of those for the population because they're Greek letters. Lowercase s for the sample standard deviation, s squared for the sample variance. N is going to be the number of values. E is still going to be our margin of error. And now we have our chi-squared values for our L and R, for our left-tailed critical value for L, and there's a typo there, the R1 should be the right-tailed critical value. So we know how to find our critical values. Let's talk about our requirements to even be doing this confidence interval. So as has been the case in all of these, we need our sample to be a simple random sample. And our second requirement this time is going to be that our population must have normally distributed values. All right, so the requirement of a normal distribution is much stricter here than it has been in earlier sections. So large departures from normal distributions can result in large errors. All right, so notice we don't have the sample size option here. Just it has to be normally distributed. If it's not normally distributed, your answer at this point is, sorry, I don't have the tools, I can't do it. It's not normally distributed, the end. All right, so our confidence interval, what it looks like, we have n-1 times our sample variance divided by our right-hand limit critical value. All right, right tail critical value. And then we have n-1 times our sample variance divided by our left-hand critical value. Notice the right hand and the left hand are on opposite sides. So the right hand or right-tailed one is on the left, and the left-tailed one is on the right in this calculation. If you get that backwards, common sense should help you fix that. All right, but it's good to remember that it goes backwards from what you might think. And lucky for us, standard deviation has always been the square root of variance. So all of this is for the variance, and nothing has changed. Take the square root of everything, and we get the sample standard or the population standard deviation estimate for our confidence interval. So you only need to remember one of them and remember the relationship between population variance and population standard deviation, and you're good to go. So our rounding. How are we going to round? Well, if we're using our original set of data, we're going to round with one more decimal place, same rule that we had for finding our variance and standard deviation to begin with. And if we're using our summary statistics, we're already using like the sample standard deviation. That rounding rule has already occurred, so we're going to use the same number of decimal places. So our procedure for constructing a confidence interval for our standard deviation or variance. All right. First thing, we're going to verify our requirements. We have simple random sample and it's normally distributed. All right. Then we're going to use n-1 degrees of freedom and find our critical values for the right tail and the left tail that correspond to the desired confidence level. Then we're going to use our formula that we have to find our interval estimate for our variance. And if we want a confidence interval for our standard deviation instead, we're going to take a square root of everything, and then we're going to apply our round-off rule. So confidence intervals can be used informally to compare the variation in different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions about equality of variances or standard deviations. So as you are interpreting this stuff or looking at the way people have interpreted it, be careful that anytime people are saying something about equal variances between things, it might be a little bit fishy, so be skeptical. So let's take a look going back to that example that we had before, where we were looking at the 22 IQ scores. We found our left and right already, critical values, and so this data is actually available in Appendix B of the book, and the standard deviation is 14.29263. So we're going to consider the sample to be a simple random sample. We're going to say, yeah, it is. And we're going to find a 95% confidence interval estimate for the standard deviation of the population. So the first thing we need to do is check our requirements. Number one, sample can be treated as simple random sample. We said, yeah, we're assuming that. Hopefully it's pretty obvious when you should be assuming that and not. Should be stated. When in doubt, again, be skeptical. All right. And number two, we look at a histogram of the data that's provided. There it is. It looks pretty close to a bell-shaped curve, so we say it's normally distributed, or approximately normally distributed. So now we're ready to move on to step 2. So using table A4 and our sample size of 22, we used 21 degrees of freedom, and we already found these chi-square values for our left tail and right tail of 10.283 and 35.479. So now using those values, we're going to find our lower and upper limits for our population variance. So n-1 is going to be 22 minus 1. Our sample variance is going to be 14.29263 squared. And remember, we take our right-tailed limit for the lower one and our left-tailed one for the upper one. And we've got this beautiful thing. We do some arithmetic, and we get a confidence interval of 120.9 and up to 417.2. So there we have our 95% confidence interval for our population variance. However, we weren't looking for the population variance, we were looking for the population standard deviation. So we take the square root of each of these and we find the 95% confidence interval for the population to be 11.0 and 20.4. So something between those values. If you get that left tail and right tail chi-square values, critical values, backwards, what you're going to end up with is 417.2 is less than sigma squared, less than our population variance, is less than 120.9. That doesn't make sense because 417.2 is not less than 120.9. That's your cue that you probably did them in the wrong order, all right? That you didn't make that switch. So check that out. Make sure your inequality order always makes sense. So now that we have all of this, we can interpret it. So based on this result, we have 95% confidence that the limits of 11.0 and 20.4 contain the true value of, that should be a sigma instead of an S. We're looking for the population standard deviation. The confidence interval can also be expressed as an interval notation of 11.0 to 20.4, not inclusive. But it cannot be expressed as our standard deviation of our sample plus or minus some margin of error. No, we didn't ever really calculate a margin of error here, right? Like we were looking instead at these left tail and right tail critical values separately. So determining sample sizes. The procedure for finding the sample size necessary to estimate our population standard deviation are much more complex than the procedures given earlier for means and proportions. So for normally distributed populations, we have a table that can help us out. It's going to be in the following slides. It's table 7.2 in the book that you can also look up. But the following formula can also be used here. But we're going to stick to the table. So, finding our sample size. To be 95% confident that our sample standard deviation is within whatever percent, right, of the population one, then the sample size that we need is given there. So if we want to be within 1%, we need 19,205 participants elements, all right? If we only want to be within 50%, then 8's enough. That's how we're reading this table, all right? If instead we want to be 99% confident that our sample standard deviation is within whatever of these percents, our sample sizes are much larger that we need. So technology can also help us out with finding sample sizes. We're not going to deal with that. So let's take a look at an example. We want to estimate the standard deviation of all IQ scores of people with exposure to lead. We want to be 99% confident that our estimate is within 5% of the true value of our population standard deviation. So how large should our sample be? We're going to assume that the population is normally distributed. So 99% confident, 5% of the true value. So we go to the table that says to be 99% confident, and we want to be within 5%, and we look at the sample size that's given there. It's 1,338. So from the table, we're finding the sample size, and it says 1,336 here. It's really 38. So we need 1,338 participants to obtain this estimate of our population standard deviation.